Hi, hello. My name is Yongneng Wu. I'm a graduate student from Dr. Ship's group, and I'm glad to join the Camp 2020 Technical Symposium even virtually. So I'm gonna give you guys a very brief of what I'm trying to do. So today my topic is cell-containing copolymers synthesis and characterization. So start with a little bit of background of cell click chemistry. So cell is actually a very reactive functional compound. And in lots of polymeric material system, people use cell X reactions to design or achieve certain cross-linking to achieve certain properties of the material. So as you can see here, there's a lot of cell X reactions can be applied. And one of the two important reactions, one is the cell in reactions and one is the cell micro additions. And the mechanisms are shown here. So because the cell is extremely useful, so polymer chemists is always trying to incorporate the cell into a polymer. However, since cell is extremely sensitive to the radical, it's basically impossible to directly do the radical polymerization of some cell-contained monomers. So how are we going to achieve cell-containing polymer? We can use the protected cell strategy. So cell lactone is basically a ring compound containing one cell and the carbonyl group. One of the most important chemical property of cell lactone is it can do the monocis, aminosis with primary amine to reopen this lactone ring, so it can generate amide and sial. So basically, the idea of my work is to synthesize a cell lactone containing monomers and polymerize that monomers, so which the polymer backbone will have cell lactone functional group. Then we treat that polymers with primary amine to reopen the cell lactone ring, so we can generate a cell on the backbone of the polymer. So pretty much that's it. About the applications. So as you can see, for cell X reactions, it's been widely used to make cross-linking polymer network. It's being used to functionize the particles and even used in the surface modification. But most of these applications actually use the small cell molecules. Like here is a pattern P. All right, like here is like 1,0-11 cell. That's all small cell molecules. So once we get the cell containing polymers, we substitute those cell small molecule to polycell. Maybe we can achieve some amazing materials. All right, so my work basically starts with a monomer synthesis. So the monomers I synthesize basically is acrylamide-like cell lactone. So start with the cell lactone hydrochloride. It's a very cheap, commercially available compound, naturally exists and react with acryl chloride. It's very simple one-step reactions. I did these reactions in 1,4-dioxane and the water's 1:1 ratio as solvent, so we can yield this cell lactone acrylamide monomer. As you can see, it looks like a white crystal, and the AMR basically prove the successful synthesis of this monomer. So next step is we just need to convert these monomers to polymers. We don't want to directly just polymerize the cell lactone acrylamide monomer because it's not that easy to get. So we choose to do some co-polymerization. One of the concern is we can lower the cost. Another concern is we adding another monomers in, we can actually tune the hydrophobicity of the final copolymer. So by tuning the hydrophobicity, we can change its application field. So it's kind of interesting and useful. So in today's case, I'm going to use the tetrabutyl acrylate as the comonomer to co-polymerize with cell lactone acrylamide, use Raft polymerization. So we can actually get good control of the molecule weight. So here is the general reaction scheme. So once we get this copolymer, actually we can react with primary amine. So in today's case, I'm going to use benzoamine or propylamine to ring open the cell lactone ring. So in the end, we can achieve the cell a polycell. And one more interesting part is once these copolymers react with primary amine, the primary amine also gonna remove one end of the raft agent. So this trisial carbonate gonna be get rid of and remaining as Sil2. So first thing, I did a little bit copolymerization kinetic study. As you can see here, I basically run the reactions with 9:1 molar ratio of the tertiary butyl acrylate to sial-lactone acrylamide, and total monomer to raft agent ratio is 100:1. And the raft agent to the initiators ratio is 10:1. And I took sample out for running AMR and the GPC every 30 minutes. So as you can see, here's an AMR graph. Actually, those vinyl protons be getting lower and lower, so which is good, right? We can see the monomers converting to the polymers. And from the GPC curve, we can see the molecule weight is actually growing. So once I calculate those data, here's the 3 kinetic graphs I get. So on the most left one, you can see the reaction time versus this low initial concentration over the certain time concentration. So basically, it's a first order kinetic graph. So both monomers shows a relatively straight linear relationship. So we can say by using the raft agent, we get a good control of this polymerization. So we calculate the propagate kinetic, the propagate constant of both monomers. For tertiary butyl acrylate, it's actually 0.00708 minutes minus 1, and for sial-lactone acrylamide, it's actually 0.01405. All right, and the second graph and the third graph is basically the conversion of each monomers to its molecule weight and to its polydispersity. So from the polydispersity, we can see during the whole reaction time, it's actually remain pretty stable. It's around 1.2-ish. It's pretty low. So we can say during this whole time, the polymerization is get good controlled by this raft agent. And the relationship between the molecule weight and the conversion for both monomers shows a linear relationship. Another proof for the good control. So it's very nice reactions we run. So actually we get a lot of this copolymer. And then I did some solubility test of this copolymer. It's actually just gonna not dissolved in water. For most common organic solvent, it shows soluble. So if we change the tertiary butyl acrylate to some other monomer like dimethyl acrylamide, we can change the solubility very easily. Or maybe we can even tune the ratio between these two monomers, because the sial-lactone acrylamide is acrylamide-like monomers get different solubilities than tertiary butyl acrylate. So the whole idea is by changing the comonomer or changing the monomer feeding ratio, we can tune the hydrophobicity, and by that we can design its application. So now, once we get the sial-lactone containing polymers, the most important thing is, okay, we're gonna react with primary amine and reopen that ring to achieve the polysial. So this reactions is gonna done in the some reducing agent. Here I use a DTT. So basically, because once the sial has been formed, it's going to be very easy for it to oxidize to form the disial from the disulfide bond. We don't want that. So I use some DTT as a reducing agent, react at the room temperature for 24 hours, and in the end, I just add a lot of acetic acid to make sure all the sial is sial, not sialate. All right, so from the AMR, we can see the actually very good modification. So I can see the peak around 3.2-ish from the sial-lactone copolymers is completely disappeared. So this peak represents the sial-lactone ring proton. And from the benzoamine modification, you can see the benzo peak. And from the propylamine modification, you can see this propyl group's peak shows up. So actually it proves a very good modification to get the polysial. All right, now for the GPC, I run before and after the primary amine modification. The interesting thing of this data is actually the dispersities didn't change too much. So because the dispersity remained pretty same, I can say there's no disulfide bond being formed during this reaction. However, the molecule weight basically is doubled. So there's a two theory, and I'm not sure which one gonna cause this data now. So one theory might be when the reactions happens, this sial gonna coupled. So basically two polymer chain gonna combine to one. That's one possibility. Another possibility is once sial being released, it might gonna do something with THF-GPC column. So that's gonna make all the retention time behave weird. I'm not sure. In my future work, I'm gonna do more research to find out why this caused the problem. But overall, I can say this reactions is being achieved. I'm able to get some polysial. And in the end, I can use this polysial to react with polyanhydride to make the network. So this whole network can use to do the water degradation for some molecule release. So that's why it's important to tune the hydrophobicity of the sial polysial or sial-containing monomer. All right, so that's all. And in the end, I want to thank Professor Devon Ship to providing me the resources and opportunity for doing this amazing research. And I also want to thank all my lab mates for their support. And in the end, I'm really thanks Clarkson University providing my teaching assistantship. And I'm glad to join the camp symposium. Hope you guys enjoy this video. Thank you.